Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Here's something truly mind-blowing that's happening to you right now, and you don't feel a thing, you're spinning. Not just a little bit, but incredibly fast. Right now, as you listen to this, you are hurtling through space on the surface of a planet that is rotating on its axis at speeds of up to 1,000 miles per hour, depending on your latitude. But that's just the beginning. This spinning Earth is simultaneously orbiting the Sun at an astonishing average speed of about 7,000 miles per hour. And our Sun, it's not sitting still either. It's part of the Milky Way galaxy, which itself is rotating, carrying our entire solar system around the galactic centre at approximately 500,000 miles per hour. And even the Milky Way isn't stationary. It's moving through the universe, influenced by the gravitational pull of other galaxies, all of them also spinning. From the grandest galaxy down to the tiniest subatomic particle, the universe is a symphony of perpetual rotation. It's as if the cosmos can't sit still, constantly twirling, swirling and pirouetting on every conceivable scale. We spend our lives on a rapidly spinning sphere, oblivious to the immense cosmic dance we're a part of, because everything around us is also moving at the same dizzying speeds. It's a fundamental property of existence, a cosmic secret whispered by every celestial body and every quantum fluctuation. Why is everything spinning? Why does the universe seem to abhor stillness, choosing instead an eternal intricate ballet of rotation? That's the profound mystery we're going to unravel, one fascinating layer at a time. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing this exploration of scientific wonder is reaching people all over the world at all hours of the day and night, connecting us through shared curiosity. Let's start with a revelation that, once you truly grasp it, will fundamentally alter your perception of reality. The universe, at its core, is a place of perpetual motion, and a significant portion of that motion is rotational. Here's what nobody tells you explicitly. We live in a universe obsessed with spinning. It's not just a few things here and there, it's practically everything. From the vast, sprawling arms of galaxies to the invisible dance of electrons within an atom. Rotation is a universal constant, a fundamental characteristic of cosmic existence. This isn't just a coincidence, it's a profound clue to how the universe works, and it's far more intricate and surprising than you might imagine. To truly appreciate this, let's build our understanding from the familiar outward. We already touched on our own planet. The Earth is a magnificent spinning top, completing one full rotation approximately every 4 hours. If you're near the equator, you're travelling at roughly 1,037 miles per hour due to this spin. As you move towards the poles, that speed decreases, but the rotational motion is undeniable. This rotation is what gives us our day and night cycle, a rhythm so fundamental to life that we often take its underlying mechanism for granted. But the Earth isn't just spinning, it's also hurtling through space in an elliptical orbit around the Sun. This orbital journey takes approximately 3 days, and during that time our planet covers a staggering 584 million miles, moving at an average speed of 6,000 miles per hour. Now, zoom out further. Our Sun, the star at the centre of our solar system, is also spinning. It doesn't spin as a solid body like Earth. Being a massive ball of plasma, its equator rotates faster than its poles, completing a rotation in about 25 Earth days at its equator, and about 35 Earth days near its poles. This differential rotation is crucial for generating its powerful magnetic fields and phenomena like sunspots. And the Sun, with all its planets, including ours, is engaged in an even grander rotation. It's orbiting the supermassive black hole at the centre of the Milky Way galaxy, Sagittarius A. This galactic orbit is immense, taking our solar system approximately 230 million years to complete one full revolution, all while travelling at an average speed of roughly 500,000 miles per hour. Think about that. The last time our solar system was in this exact spot in the galaxy, dinosaurs were just beginning to emerge. This pattern isn't unique to our solar system or our galaxy. Look out into the cosmos, and you'll find that nearly every galaxy we observe is spinning. Spiral galaxies, like our Milky Way, are perhaps the most visually striking examples, with their magnificent arms spiralling outwards, a clear testament to their rotational motion. But even elliptical galaxies, which appear more amorphous, possess internal rotation, though often less organised. These galaxies are colossal collections of stars, gas, dust and dark matter, all bound together by gravity, and all engaged in a collective gargantuan spin. For instance, the Andromeda Galaxy, our closest large galactic neighbour, is also a spiral, and it rotates with its outer regions moving at speeds upwards of 20 miles per second. The scale here is almost incomprehensible. Billions of stars, each a sun in its own right, spinning around at a common centre, all while the entire structure rotates through the intergalactic void. The ubiquity of spin extends downward too. Inside our solar system, almost all the planets are spinning on their axes, though with varying speeds and tilts. Jupiter, the largest planet, spins incredibly fast, completing a rotation in less than 10 hours, creating its characteristic banded appearance. Saturn, with its iconic rings, also spins rapidly. Even the moons around these planets, many of them, exhibit their own rotations. The formation of these systems, from the vast nebulae collapsing into stars and planets, inherently involves rotational dynamics. Our solar system itself was born from a spinning disk of gas and dust, and the conservation of that initial angular momentum dictated how the planets formed and continue to move. But here's where it gets truly mind-bending. This phenomenon of spin doesn't stop at macroscopic objects like planets and stars. It delves into the very fabric of matter itself. When we talk about the fundamental particles that make up everything, electrons, protons, neutrons, we also talk about spin. Now, this isn't a classical spin like a tiny top rotating on its axis. These particles are not little miniature spheres that are physically twirling. Instead, Semlin quantum mechanics refers to an intrinsic angular momentum, a fundamental property of the particle, much like its mass or electric charge. It's a quantum number, a label that describes how the particle behaves in a magnetic field, for instance. Electrons, for example, have a spin of 1/2, meaning they can align in one of two directions, often colloquially called spin up or spin down. Protons and neutrons, which are made of even smaller particles called quarks, also possess this intrinsic angular momentum. So even at the most foundational level of reality, the concept of spin persists, a ghostly echo of the cosmic whirl. The universe, then, is not merely in motion, it's revolving. It's not just moving from point A to point B, it's constantly turning around an axis. Whether that axis is the centre of a galaxy, the core of a star, or an abstract quantum property of a fundamental particle, this raises a profound question. Why? Why is spin so pervasive? Where did all this rotational motion come from? Could it be that the very genesis of the universe, the Big Bang itself, imbued everything with an initial fundamental twist? Or is there a deeper, more elegant principle at play that ensures nothing can truly sit still in the vast cosmic expanse? This universal tendency towards rotation is not merely an observational curiosity, it's a fundamental consequence of how mass, energy, and gravity interact. The answer is in one of the most powerful and beautiful conservation laws in physics, the conservation of angular momentum. This principle dictates that rotational motion, once started, tends to persist unless acted upon by an external force. In our next chapter, we'll delve into this crucial law, exploring how it governs everything from the pirouetting ice skater to the formation of entire galaxies, and how it provides the initial powerful clue to understanding why everything in the universe is spinning. Welcome back, cosmic explorers, to Dreamy Science, where we unravel the universe's most profound mysteries, one captivating question at a time. In our last chapter, The Cosmic Whirl, we started to truly grasp the mind-blowing reality that everything in the universe is spinning, from the Earth beneath your feet to the distant galaxies hurtling through the void, and even the fundamental particles that make up your very being. We marveled at this universal obsession with rotation, this intricate, eternal ballet of motion. But we left you with a cliffhanger, a promise that the key to understanding why everything spins lies in one elegant, immutable law, the conservation of angular momentum. And that, my friends, is where our journey truly deepens. We're about to delve into a concept so fundamental, so beautifully simple yet profoundly powerful that it shapes the very architecture of the cosmos. This isn't just some abstract physics equation, it's the invisible hand guiding the universe's most spectacular performances. So what exactly is angular momentum? Think of it this way. Linear momentum is about something moving in a straight line. A bowling ball rolling down an alley. Angular momentum, on the other hand, is about something spinning or orbiting. It's a measure of how much rotational motion an object has. It depends on three key things: how fast something is spinning, its angular velocity, how much stuff it's made of, its mass, and crucially, how that mass is distributed relative to its axis of rotation, its radius or moment of inertia. Imagine a planet. It has a certain mass, it spins at a certain speed, and that mass is spread out across its diameter. All these factors combine to give it angular momentum. Now for the truly mind-bending part, the conservation of angular momentum. This is one of the most bedrock principles in all of physics, right up there with the conservation of energy and linear momentum. What it tells us is this: in a closed system, the total angular momentum remains constant. It can't be created and it can't be destroyed. It can only be transferred from one object to another or redistributed within the same object. Think of it like this. You can't make something spin out of nothing, and if something is spinning, it will keep spinning unless something else acts upon it to slow it down or speed it up. But here's where the redistribution comes in, and it's the secret sauce that explains the universe's dizzying dance. If an object's mass distribution changes, specifically if its radius shrinks, its spin must increase to keep the total angular momentum the same. Conversely, if its radius expands, its spin must slow down. Let's ground this with some familiar examples. The classic illustration is the ice skater. You've seen it 1,000 times, right? An ice skater starts a spin with their arms outstretched. They are turning at a certain speed. Then they pull their arms and legs in close to their body. What happens? They instantly start spinning much, much faster. Why? Because by pulling their mass closer to their axis of rotation, they've decreased their radius. To conserve their angular momentum, their angular velocity, their spin speed has to increase dramatically. The total angular momentum hasn't changed, it's just been redistributed. Or consider a playground merry-go-round. If you push it and then step onto the outer edge, it spins at a certain rate. Now if you slowly walk towards the centre, what do you notice? The merry-go-round starts to spin faster. You've brought your mass closer to the centre, reducing the effective radius, and the merry-go-round accelerates to conserve the angular momentum of the system. It's an everyday marvel, a quiet demonstration of a cosmic truth. Now, let's take this elegant principle and apply it to the grandest scales imaginable. This is where we truly begin to connect the dots and understand why the universe is obsessed with spinning. Imagine, if you will, a vast, diffuse cloud of gas and dust out in the interstellar medium, a nebula stretching light years across. These clouds are the nurseries of stars and planets. We're talking about incredibly tenuous stuff, far less dense than the air you're breathing. Now, even in the deepest, most tranquil parts of space, nothing is perfectly still. There are always tiny, almost imperceptible turbulences, slight currents and faint initial rotations within these enormous clouds. Perhaps a distant supernova shockwave gave it a gentle nudge, or the gravitational tug of a passing star imparted a minuscule twist. We're talking about a rotation so slow, so subtle you wouldn't even notice it. But then gravity enters the scene. Over millions of years, gravity begins to pull the gas and dust particles in the cloud closer together. As the cloud collapses, its overall size, its radius, begins to shrink. And what happens when a spinning object's radius shrinks, according to our principle of conserved angular momentum? Its spin must increase. As this protostellar cloud continues to collapse under its own immense gravity, it spins faster and faster, just like our ice skater pulling in their arms. This increasing centrifugal force pushing outwards prevents the cloud from collapsing into a single point. Instead, it flattens into a rotating disk, with a dense, hot core forming at the centre, our nascent star. This is why we see protoplanetary disks around young stars, and why our own solar system is a relatively flat disk, with planets all orbiting in roughly the same plane and direction. The initial, barely there rotation of that ancient nebula got amplified, concentrated, and flattened into the spinning sun and orbiting planets we observe today. Every planet, every moon, every asteroid in our solar system is a ghostly echo of that initial cosmic whirl. This isn't just about individual stars and their planetary systems, it's about galaxies too. Scale up that process exponentially. Imagine the early universe, after the Big Bang. It wasn't perfectly smooth. There were tiny, minute density fluctuations, slight variations in the distribution of matter. And within these vast primordial clouds of hydrogen and helium, there were also incredibly faint initial rotations. These could have been imparted by the turbulence of the early universe itself, or even by quantum fluctuations that got stretched to cosmic scales. Over billions of years, gravity started to work its magic on these enormous, diffuse clumps of matter. As these colossal structures began to coalesce, pulling in vast amounts of gas, dust, and dark matter, their immense radii began to shrink, and just like the collapsing nebula, their initial, almost imperceptible rotations were amplified, spinning them faster and faster. This is how galaxies form their characteristic disk shapes and spiral arms. The spin prevents them from collapsing into a single giant blob, flattening them into the spectacular rotating cosmic pinwheels we observe across the universe. Our own Milky Way, a magnificent barred spiral, is a testament to this fundamental law. Its 200 billion stars and countless nebulae, all participating in a grand gravitational dance around the supermassive black hole, Sagittarius A, at its heart. It's truly awe-inspiring, isn't it? The conservation of angular momentum is the universal choreographer. It takes whatever tiny initial spin exists and, through the relentless pull of gravity, transforms it into the rapid rotation of stars, the orbital dance of planets, and the majestic swirl of galaxies that explains why. The cosmos is a symphony of perpetual rotation, a dynamic, ever-moving marvel. But here's the crucial point, and it leads us to our next grand question. The conservation of angular momentum explains how existing spin gets amplified and redistributed. It explains why things spin faster as they get smaller, but it doesn't explain where that initial tiny bit of spin came from in the first place. This law tells us that angular momentum is conserved, meaning if there's no initial spin, there will never be any spin. So if everything is spinning, it implies that the universe, at its very inception, must have possessed some inherent fundamental rotation, however minuscule. This is the ultimate origin story of spin, and it takes us back to the very beginning, to the Big Bang itself. What imparted that first infinitesimal twist to the fabric of space-time? Was it an inherent property of the early universe's expansion? Were there tiny quantum mechanical fluctuations that, when stretched across the cosmos, became the seeds of galactic rotation? The universe, it seems, wasn't born perfectly still. It was born with a subtle, primordial swirl, cosmic tremor that set the stage for everything that followed. We've peeled back another layer of the cosmic onion, revealing the elegant mechanism that powers the universe's spin. We understand now that the universe isn't creating spin, it's preserving it, amplifying it and shaping it into the wonders we observe. But the question of that initial spark, that first whisper of rotation, still beckons. It's a profound mystery, a journey into the very infancy of existence, and one we'll continue to explore together. I hope you're feeling that sense of wonder, that deep connection to the forces that sculpt our reality. If you're enjoying this cosmic journey, I'd love it if you'd hit that like button. Consider subscribing to Dreamy Science. Your curiosity fuels these explorations, and I'm always curious to hear your thoughts in the comments below. What aspect of the universe's spin do you find most fascinating? Join us next time as we dive even deeper into the primordial soup, exploring the very first moments of the universe to uncover the ultimate source of that initial, all-important spin. Until then, keep looking up, keep wondering, and remember, you too are part of this magnificent spinning cosmos. We've journeyed together through the cosmic ballet, unraveling the mesmerizing truth that everything, from the smallest particle to the grandest galaxy, is caught in an eternal, intricate dance of rotation. We've seen how the incredible principle of the conservation of angular momentum acts as the universe's master choreographer, taking the faintest initial twirls and amplifying them into the breathtaking spins of stars and the majestic sweeps of galaxies. It's a truly mind-bending concept, isn't it? How a shrinking radius can transform a slow drift into a dizzying whirl, shaping the very structures we observe across the cosmos. But as we stood at the precipice of our last chapter, a profound question lingered, a whisper echoing through the vastness of space and time. Where did that initial spin come from? If angular momentum can only be conserved, not created, then what ignited that very first spark of rotation? What gave the universe its primordial twist? We've explained the how, but now we must bravely venture into the realm of the why, delving into the ultimate origins of this universal obsession with spinning. Imagine, if you will, the universe in its absolute infancy. Not a serene, still void, but an unimaginably hot, dense, and rapidly expanding soup of fundamental particles and energy. This wasn't a calm, orderly place. Oh no, far from it. This was a maelstrom, a cosmic crucible, a place of incredible, violent activity. Think of stirring a pot of boiling water, but on a scale that beggars belief, where the water is the very fabric of space-time and the stirring is the universe itself being born. In this superheated, super-dense plasma, mere moments after the Big Bang, perfect stillness and absolute uniformity were simply not options. The laws of physics, as we understand them, forbid it. At such extreme energies and densities, quantum mechanics reign supreme, dictating that even in what seems like a vacuum, there are always tiny, fleeting fluctuations. Particles pop into existence and vanish in an instant. Energy levels ripple, and the very fabric of space-time trembles with inherent, inescapable jitteriness. This is where the story of primordial spin truly begins. We're not talking about a grand, deliberate push, but a symphony of countless infinitesimal turbulences. As the early universe expanded and cooled, these tiny, random quantum fluctuations, these microscopic variations in energy and density, would have naturally given rise to areas of slightly higher pressure, slightly higher velocity, slightly higher anything. And where there are differences, where there are gradients, there is the potential for motion, for flow, for rotation. Think of it like this. If you have a perfectly smooth, perfectly still pond, it will remain still. But if even the tiniest pebble drops or the gentlest breeze whispers across its surface, ripples and eddies will form. The early universe was less like a still pond and more like a raging, frothing ocean, constantly in motion, constantly churning. These inherent turbulences, these tiny eddies and vortices within the primordial plasma, were the very first whispers of rotation. They weren't created by an external force. They were an intrinsic, unavoidable consequence of the universe's quantum birth. Now, let's zoom out a bit and consider the mind-bending concept of cosmic inflation. This is a theoretical period, theorized to have occurred fractions of a second after the Big Bang, during which the universe expanded at an absolutely staggering exponential rate. We're talking about expanding by factors of 10 to the 26 or more in an unbelievably short span of time. What does this have to do with spin? Everything. Remember those tiny quantum fluctuations we just talked about? In a normal, slow-expanding universe, these fluctuations would remain microscopic. But during cosmic inflation, these infinitesimal ripples were stretched and amplified to astronomical scales. Imagine a tiny wrinkle on a balloon suddenly becoming a vast mountain range as the balloon inflates at an unimaginable speed. That's what inflation did to these quantum fluctuations. It took the inherent random jitteriness of the early universe and imprinted it onto the very large-scale structure of the cosmos. So those tiny primordial turbulences, those faint eddies of rotating plasma, weren't just localized phenomena. They were stretched and solidified into the initial conditions for the universe we see today. These weren't perfectly uniform, perfectly still regions. They carried within them the ghostly echo of that cosmic whirl, those initial, almost imperceptible twists. As gravity began its tireless work pulling together these slightly denser regions of matter and energy, it encountered these already slightly rotating systems. And what happens when a rotating system collapses? You guessed it. The conservation of angular momentum kicks in, amplifying those minuscule inflationary stretched rotations into the powerful spins that would eventually give birth to galaxies, stars, and planets. It's almost as if the universe was born with a fundamental twist, not a flaw, but an inherent characteristic. It wasn't born perfectly symmetrical, perfectly uniform, or perfectly still. It was born dynamic, with an intrinsic bias towards motion and rotation. This isn't about some external hand giving it a push. It's about the very fabric of reality at its most fundamental level, being inherently active and non-uniform. Some theories even propose that primordial gravitational waves, ripples in space-time itself, generated during the Big Bang or inflation, could have imparted rotational energy to the early universe. Imagine space-time literally twisting and swirling, carrying that rotational energy through the cosmos. These waves, if detected, could offer direct evidence of the universe's chaotic birth and its inherent rotational tendencies. We're constantly building our understanding, pushing the boundaries of what we know, and every new piece of the puzzle brings us closer to truly grasping this cosmic truth. So when we ask, why is everything spinning? The deepest answer seems to be, because the universe was born that way. It wasn't born perfectly smooth and still, waiting for some external force to set it in motion. It was born with inherent turbulence, with quantum fluctuations stretched to cosmic scales, with a fundamental, inescapable twist. This initial minuscule yet pervasive spin was then relentlessly amplified by gravity and the ironclad law of angular momentum, leading to the grand spinning spectacle we observe today. It's a beautiful, humbling thought, isn't it? That the very act of the universe coming into being carried within it the seeds of all future motion. Every rotation, from the dizzying speed of a neutron star to the majestic billion-year-long sweep of a galaxy, is a direct descendant of those first fleeting moments after the Big Bang. We are all, quite literally, products of a spinning universe, born from its initial turbulence and shaped by its relentless dynamism. This understanding profoundly shifts our perspective. We don't just live in a spinning universe, we are part of its spin, imbued with that ancient primordial motion. Our atoms, our planet, our solar system, our galaxy, all are continuing a dance that began at the dawn of time. There is no true stillness, no ultimate rest, only a perpetual, magnificent motion. This isn't just about physics. It's about poetry. It's about recognizing that the universe is a living, breathing, constantly evolving entity, forever in motion. It's a testament to the incredible, complex interplay of fundamental forces that gave rise to everything we know, and it compels us to look at the night sky, at our own world, at ourselves, with a renewed sense of wonder and connection to that initial cosmic whirl. As we stand here gazing into the vastness of this spinning reality, we realize that the universe isn't just doing something, it is something. It's a symphony of perpetual rotation, a grand ongoing experiment in motion. And the implications of this constant fundamental dynamism extend far beyond just how galaxies form. They touch upon the very nature of existence, the flow of time, and perhaps even the ultimate fate of the cosmos. But those are questions, my friends, for another chapter in our journey together. For now, let's simply marvel at the profound truth. The universe spins because it was born to spin. All right, fellow cosmic explorers, we've journeyed deep into the heart of the universe's most pervasive mystery. We've unraveled the incredible story of angular momentum, that invisible cosmic choreographer ensuring every pirouette, every orbit, every majestic spiral is preserved. We've even dared to peer into the universe's fiery infancy, discovering the primordial twist those microscopic quantum fluctuations stretched by cosmic inflation that birthed the very first whispers of spin into existence. It's truly mind-bending to think that the universe didn't just start, but it started spinning right from the get-go. But now, as we stand on the precipice of Chapter 4, we must ask, what does this all mean? Why is this universal obsession with rotation so fundamentally important? It's not just a curious side effect, my friends. What nobody tells you explicitly is that this spin, this constant, relentless motion, isn't merely a feature of our universe. It's an absolute non-negotiable necessity. Without it, the cosmos as we know it, with its dazzling galaxies, life-giving stars and habitable planets, simply wouldn't exist. Imagine, if you will, a universe without spin, a static, lifeless realm where gravity, the universe's ultimate sculptor, reigns supreme without opposition. Gravity, as we know, is a relentless force. It wants to pull everything together, to coalesce, to compact. If there were no counteracting force, no outward push, every cloud of gas and dust would simply collapse inward, forming a dense, featureless singularity. There would be no sprawling nebulae, no elegant spiral arms, no distinct stars or planets. Just an endless, uniform cosmic mush. This is where spin, our hero, enters the cosmic stage. Spin is gravity's essential dance partner, the centrifugal force that provides the outward resistance. It's the reason why a collapsing cloud of gas and dust doesn't just become a single massive blob. As the cloud shrinks under gravity's pull, its spin rate dramatically increases, thanks to the conservation of angular momentum we discussed. This increased spin generates an outward force, pushing against gravity's inward squeeze. The result? A cosmic standoff, a delicate equilibrium that sculpts the universe into the wondrous structures we observe. Think about a galaxy, for instance. We see these magnificent pinwheels, vast collections of billions of stars, gas and dust, all orbiting a central point. Why don't they just collapse into one giant supermassive black hole? Because they're spinning! The stars, just like tiny dancers on a colossal stage, are not falling directly into the galactic center. Instead, their orbital motion, their individual spins and collective rotation, creates the centrifugal force necessary to counteract the immense gravitational pull of the galaxy's core, including its central supermassive black hole, like Sagittarius A in our own Milky Way. This balance of inward pull and outward push flattens these massive structures into the iconic disk shapes we adore, a cosmic testament to the power of spin. And what about our own solar system? Why doesn't Earth plummet into the sun? Again, its spin. Our planet is in a perpetual freefall around the sun, but its tangential velocity, its orbital spin, keeps it moving sideways fast enough to continuously miss. It's a cosmic ballet, a delicate balance where gravity provides the centripetal force pulling us inward, and our orbital angular momentum provides the resistance keeping us in a stable, predictable path. Without that initial tiny bit of spin imparted to the primordial solar nebula, and its subsequent amplification as the nebula collapsed, there would be no planets, no orbits, no stable solar system, and certainly no us. This principle, this intricate dance between gravity and spin, isn't limited to the grandest scales. It permeates every level of existence. Consider the formation of individual stars. A dense pocket within a molecular cloud begins to collapse. As it shrinks, its spin rate accelerates, flattening it into a protoplanetary disk, a spinning pancake-like structure where planets will eventually form. The star itself, once ignited, continues to spin, its rotation preventing it from collapsing further under its own immense gravity. It's only when a star exhausts its nuclear fuel and the outward pressure from fusion ceases that gravity can finally begin to win, leading to dramatic stellar deaths like supernovae, or the formation of neutron stars and black holes, which themselves are often incredibly fast spinners. Now, let's take a truly mind-bending leap. We've talked about galaxies, stars and planets, but what about the very building blocks of matter? What about atoms? You might be thinking, do atoms spin? And the answer, in a way, is a resounding yes, though not in the classical sense of a miniature Earth rotating on its axis. We're talking about something called electron spin and nuclear spin. These aren't literal rotations, but rather intrinsic angular momentum, a fundamental quantum property of particles like electrons, protons and neutrons. It's as if these particles come pre-packaged with a tiny inherent twist. This quantum spin is a cornerstone of particle physics and quantum mechanics. It dictates how particles interact, how atoms bond, and ultimately, the very chemistry that allows life to exist. Electrons, for instance, have a spin that can be up or down, influencing their energy levels and how they fill atomic orbitals. This isn't just an abstract concept, it's what makes magnetic resonance imaging, MRI, possible, allowing us to peer inside the human body. So from the incredibly vast structures of the universe down to the infinitesimal realm of quantum particles, spin is an ever-present defining characteristic. It suggests a profound unity, a universal principle that threads through all scales of reality. And here's where it gets even more fascinating, stretching our understanding of space-time itself. We know from Einstein's general theory of relativity that mass and energy warp the fabric of space-time, creating gravity. But what happens when that mass is spinning? It turns out a spinning mass doesn't just warp space-time, it also drags it. This phenomenon is known as frame dragging, or the lens-thirring effect. Imagine stirring a very thick, viscous liquid with a spoon. The liquid near the spoon gets pulled along, creating a swirl. Similarly, a massive spinning object like a black hole, a neutron star, or even Earth to a tiny extent, literally drags the space-time around it, pulling it along in the direction of its rotation. This means that if you are in orbit very close to a rapidly spinning black hole, your trajectory would be subtly influenced, not just by its gravitational pull, but by the fact that space-time itself is being twisted around by its rotation. It's like being caught in a cosmic whirlpool. This isn't just theoretical speculation. Frame dragging has been experimentally confirmed by missions like Gravity Probe B. It tells us that spin isn't just about objects moving in space-time. It's about objects influencing and twisting space-time itself. It elevates spin from a mere property of matter to an active participant in shaping the very geometry of our universe. It makes spin an even more fundamental, more potent force than we might initially imagine. So when we ask, why is everything spinning? The answer begins to coalesce into something profound. Because spin is the unseen architect of stability, the silent partner to gravity, the fundamental force that allows complex structures to emerge from the primordial chaos. Without spin, there would be no galaxies, no stars, no planets. There would be no cosmic dance, no intricate ballet of rotation. The universe would be a uniform, undifferentiated blob, devoid of the diversity and dynamism we observe. Spin is what enables the universe to be vibrant, evolving, and ultimately life-supporting. It's not just a quirk, it's a condition for existence. It's the reason why the universe is a symphony of perpetual motion, an eternal, intricate ballet of rotation that has been playing out since the Big Bang, driven by that initial, primordial twist. As we ponder this incredible truth, this realization that spin is woven into the very fabric of reality, from the quantum foam to the cosmic web, we begin to appreciate the sheer elegance and interconnectedness of our universe. It challenges us to look beyond the obvious, to understand that what appears to be simple motion is actually a deep, fundamental principle underpinning everything. And as always, I'm curious, how does this knowledge shift your perspective on the world around you? Do you feel that subtle, ceaseless spin a little more acutely now? Let me know in the comments below. I'd love to hear your thoughts. Next, we're going to delve even deeper, exploring what this constant dynamism means for the arrow of time, the ultimate fate of the cosmos, and perhaps even our own perception of reality. The journey continues, and it promises to be nothing short of mind-blowing. In our journey through the perpetually pirouetting cosmos, we've unravelled the profound how of spin, tracing its conservation from an ice skater to a nascent galaxy. We've peered into the primordial twist that set the universe in motion, and we've marvelled at spin's indispensable role as the unseen architect, preventing cosmic collapse and forging the very structures that allow us to exist. But what does this ceaseless universal dynamism truly mean for everything else, for the very fabric of time itself, for the ultimate destiny of the cosmos, and perhaps most mind-bending of all, for our own perception of reality? These aren't just abstract questions for physicists to ponder in sterile labs. They are the cosmic echoes of the spin we've been exploring, reverberating through the deepest mysteries of existence. Today we're going to dive headfirst into these profound implications to see how the universe's obsession with rotation isn't just a fascinating phenomenon, but a fundamental condition that shapes our understanding of time, carves out the future of everything we know, and fundamentally alters how we perceive the world around us. So take a deep breath, because we're about to explore the truly mind-expanding consequences of a spinning universe. And the arrow of time, the universe's ticking clock. You see, for time to be time, it needs a direction. It needs an arrow, always pointing forward from past to future. But why does time only flow one way? Why do we remember yesterday but not tomorrow? At the most fundamental level, the laws of physics are largely symmetrical in time. They work just as well forwards as they do backward. Yet, our experience is unequivocally unidirectional. This is one of the universe's most enduring mysteries, often attributed to the inexorable march of entropy, the universe's tendency towards increasing disorder. But what if spin, this fundamental dynamism we've been exploring, is a silent, ubiquitous partner in this cosmic march? Imagine a universe without spin, a perfectly static, perfectly still cosmos. There would be no swirling galaxies, no rotating stars, no orbiting planets. There would be no initial turbulent eddies in the early universe, no frame-dragging, twisting space-time. In such a universe, without the constant dynamic interplay of rotating masses, without the inherent gradients and changes that spin creates, would there even be a clear arrow of time? A perfectly uniform, unchanging system has no before or after, no distinct states to differentiate. It's the constant complex dance of rotating and orbiting bodies, the ceaseless rearrangements of matter and energy driven by angular momentum that provides the fuel for change, for interaction, for the very progression of events that defines time. Think about it. The very process of star formation, driven by a collapsing, spinning nebulae, is a temporal event. The evolution of a galaxy, its arms spiraling and stars being born and dying as a temporal sequence. Even at the quantum level, the spin of particles dictates their interactions, their movements, their transformations, all processes that unfold in time. The universe isn't just expanding, it's expanding while spinning, creating new structures, new complexities, new opportunities for disorder to increase in specific, localized ways, even as the overall energy of rotation is conserved. The constant creation and dissipation of energy through these rotational dynamics contribute to the overall entropy of the system, providing the very engine for time's forward march. Without this inherent dynamism, this primordial twist, the universe might be a frozen, timeless tableau rather than the vibrant, evolving tapestry we inhabit. It's almost as if spin is the universe's very first, most fundamental clock hand, constantly sweeping forward, ensuring that now is always distinct from then. Spin in the cosmic destiny. The universe's perpetual gyroscope. If everything is spinning, what does that mean for the ultimate fate of the universe? We've discussed the grand, sweeping possibilities, the big freeze, the big rip, the big crunch. But how does this pervasive angular momentum, this conserved rotational energy, play into these cosmic finales? Consider the immense energy locked up in the universe's spin. Every galaxy, every star, every planet, every black hole is a reservoir of angular momentum. This isn't just a static property. It's dynamic energy, constantly interacting, constantly influencing. As galaxies merge, their supermassive black holes coalesce, spinning ever faster. Their event horizons twisting space-time with increasing ferocity. This process isn't just about mass accumulation. It's about the combination and redistribution of vast amounts of angular momentum. The very structure of these merging systems, their eventual shape and dynamics, are dictated by the conservation laws we explored in Chapter 2. In a big freeze scenario, where the universe expands indefinitely, cools, and becomes increasingly dilute, what happens to all that spin? Even as stars burn out and black holes evaporate via Hawking radiation, the angular momentum doesn't simply vanish, it's conserved. The remnants of the universe, perhaps ultra-cold, ultra-dilute particles, or even just the fabric of space-time itself, would still carry the ghostly echo of the cosmic whirl. Imagine a universe so vast, so empty, that the distances between particles are astronomical, yet each particle, each quantum speck, still retains its fundamental quantum spin. The universe, in its dying embers, might still be a giant, incredibly diffuse, perpetually turning gyroscope, its inherent rotational energy an eternal, albeit increasingly rare, hum. Conversely, if the universe were destined for a big crunch, where gravity eventually triumphs and pulls everything back together, spin would play a crucial, perhaps delaying role. The outward centrifugal force generated by all that rotation would actively resist collapse, much as it prevents stars from falling in on themselves. A universe with significant angular momentum would be harder to compress into a singularity than a perfectly static one. It might bounce, or it might simply slow the crunch, creating a more complex, drawn-out cosmic recollapse. The universe, in its very essence, is built to resist stillness, and this resistance, powered by spin, will likely be a defining feature of its ultimate fate, whatever that may be. It's a universe that even in its twilight refuses to stand still. Spin and our perception of reality, the illusion of stillness. Now, let's bring this cosmic dance back down to Earth, back to you. What does it truly mean to live in a universe where absolutely everything is spinning all the time? It means that your sense of stability, your perception of stillness, is an intricate, beautiful illusion. You're sitting or standing or lying down right now, perhaps feeling perfectly still, well, we know better, don't we? You're spinning with the Earth at over 1,000 miles per hour. You are hurtling around the sun at 10,000 miles per hour. You and everything around you are being swept through the galaxy at 500,000 miles per hour as our entire Milky Way spirals through the cosmos. And at the microscopic level, the atoms that make up your chair, your clothes, your very body, are composed of particles with intrinsic quantum spin, constantly engaged in their own subatomic ballet. Your entire reality is built upon a foundation of relentless, dizzying motion. The solid ground beneath your feet is a rapidly rotating sphere. The seemingly fixed stars are distant suns, many of them spinning themselves, all part of a larger galactic whirl. Even the light that allows you to read these words is a wave of electromagnetic energy, intrinsically linked to the spin of the photons that carry it. Our senses are wonderfully adapted to this dynamic reality. We perceive change, motion, and interaction. A truly static universe would be featureless, devoid of the gradients and transformations that allow for perception and consciousness. It's the constant subtle shifts in position, the interplay of forces, the very act of objects moving relative to one another, all influenced by spin, that creates the rich tapestry of sensory experience. The fact that we can perceive stability amidst this cosmic maelstrom is a testament to the incredible sophistication of our brains, which filter and interpret this constant motion into a coherent, livable reality. So the next time you feel a sense of calm, a moment of stillness, take a moment to truly grasp it. Understand that this tranquility is not an absence of motion, but a harmonious balance of countless spins and rotations, a perfectly orchestrated symphony of perpetual movement that allows for the very possibility of your existence, your thoughts, your perceptions. You're not just in a spinning universe, you are a spinning universe, a microcosm of the cosmic dance, an intricate eddy in the grand eternal current. This realization isn't meant to make you dizzy, but to fill you with a profound sense of awe. It's a testament to the universe's inherent dynamism, its refusal to ever truly stand still. We've journeyed from the familiar spin of a top to the mind-bending implications for time, destiny, and perception. And yet, for all we've discovered, the universe's ceaseless spin continues to whisper new questions, new mysteries, inviting us to look a little closer, to feel a little more deeply. The cosmic whirl that defines everything. What other secrets does this eternal ballet hold? We're only just beginning to truly grasp the magnitude of it all. And so, we stand on the precipice of an even grander revelation. Chapter 5 left us with the profound realization that our everyday stillness is nothing but a masterfully orchestrated illusion, a harmonious ballet of countless relentless spins. You, me, the chair you're sitting on, the very air you breathe. All of it is a microcosm of this cosmic dance, perpetually in motion, forever twirling. It's a mind-bending truth, isn't it? One that forces us to reconsider the very fabric of our perceived reality. But what if this isn't just an elegant byproduct of physics? What if spin isn't merely a mechanism for structure or a driver of time, but something far more fundamental, something woven into the deepest secrets of existence itself? What if it's a key to unlocking mysteries that transcend our current understanding of the universe, pointing towards broader implications we've only just begun to glimpse? This is where our journey takes an even more speculative yet utterly exhilarating turn. Today, we're going to delve into the whispered theories at the edge of science, exploring how spin might be intimately connected to the very nature of information, consciousness, and perhaps even the hidden dimensions that could make up our cosmos. We're stepping into the realm where physics meets philosophy, where the tangible whirl of a galaxy might echo the intangible twist of reality itself. Get ready, because what we're about to explore could fundamentally shift your perspective on everything. Let's begin with a concept that increasingly fascinates physicists: information. We often think of the universe as being made of matter and energy, but what if information is just as fundamental, perhaps even more so? Every particle, every field, every interaction carries information. A photon's polarization, an electron's charge, a proton's mass. These are all bits of information encoded in the universe's fundamental language. And within this cosmic library, what's one of the most crucial pieces of information carried by every fundamental particle? You guessed it. Spin. Think about it. Quantum spin isn't just a random property. It's a precisely defined characteristic that distinguishes particles, dictates their interactions, and plays a critical role in the very structure of atoms. It's a binary state, up or down, a fundamental bit of information that the universe uses to build itself. Without these distinct spin states, the Pauli exclusion principle wouldn't work, and atoms as we know them couldn't exist. Life in turn couldn't exist. So in a very real sense, spin is a foundational unit of information upon which all complexity is built. Now, let's zoom out to the cosmic scale. Consider black holes. These enigmatic devourers of light are also, paradoxically, considered the most efficient information storage devices in the known universe. When matter falls into a black hole, its information isn't lost. It's thought to be encoded onto the black hole's event horizon, perhaps in the form of quantum entanglement or other subtle properties. And what's a defining characteristic of most black holes? You guessed it again. Spin. A rotating black hole, also known as a Kerr black hole, drags space-time around it, creating a region called the ergosphere, where even light cannot remain stationary. Its spin defines its geometry and its interaction with the surrounding universe. Is it too far-fetched to wonder if the universe itself, in its grandest manifestation, is a colossal information processing system, and spin is its fundamental operating language? If everything from the quantum foam to the galactic supercluster is spinning, and if spin inherently carries information, then the universe is not just moving, it's constantly computing, constantly evolving its own internal state. Your very thoughts, the electrical impulses in your brain, are themselves orchestrated by the quantum spins of countless electrons and protons. Could consciousness itself, that most elusive of phenomena, be an emergent property of this universe-wide, spin-driven information network? It's a truly mind-bending thought, suggesting that our awareness isn't just happening in the universe, but is perhaps an intricate part of the universe's own self-awareness, expressed through the eternal dance of spin. But the implications don't stop there. What if spin isn't just about information within our three spatial dimensions? What if it's a gateway to understanding the universe beyond what our senses can perceive? We touched upon frame dragging in Chapter 4, the idea that massive spinning objects twist the very fabric of space-time around them. It's a subtle but profound effect predicted by Einstein's general relativity, a ghostly echo of the cosmic whirl that distorts the geometry of the universe in its vicinity. Now, imagine this. What if these subtle twists and turns, these gravitational eddies caused by spin, aren't just local distortions, but hints at a deeper, multi-dimensional reality? Theoretical physics has long toyed with the idea of extra-spatial dimensions, dimensions curled up so tightly we can't perceive them, or perhaps vast and parallel like brains floating in a higher dimensional bulk. Could the pervasive spin we observe in our universe be a signature, a vibrational hum, an energetic resonance that connects us to these hidden realms? Picture our universe as a spinning top. If there are other tops spinning alongside ours, perhaps in different orientations or at different speeds, then the way our universe spins, the very direction and rate of its rotation, could be a unique identifier, a cosmic fingerprint that distinguishes it within a vast multiverse. Could the spin of our entire universe, if it has one, be what defines its particular brain, its specific energy signature, its very existence within a higher dimensional reality? We're talking about concepts that are purely speculative, yes, but they spring from the very real and observable phenomenon of spin. If gravity can twist space-time and spin is intrinsically linked to gravity's effects, then perhaps spin is one of the fundamental mechanisms through which dimensions interact, or through which the architecture of a multiverse is constructed. It suggests that the spin you feel in your own cells might be a tiny personal echo of a much grander, multi-dimensional gyration. This leads us to perhaps the most ambitious question of all. Is spin more than just a property or a consequence? Is it in fact a fundamental constant, or even an undiscovered fifth fundamental interaction that shapes the very architecture of existence? We know of four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. Each governs specific interactions and scales, but spin, while often described as an intrinsic property or a manifestation of angular momentum conservation, seems to permeate everything in a way that feels more fundamental than just being a result. It's present at the quantum level, defining particles. It's present at the cosmic level, shaping galaxies and preventing universal collapse. It's tied to information, to time, and potentially to the very structure of space-time itself. Its influence is ubiquitous, its necessity absolute. It doesn't just happen, it is. Could it be that what we perceive as spin is simply our current limited understanding of a deeper, pervasive interaction that we haven't yet fully categorized? A subtle, ever-present force that maintains the dynamic equilibrium of the cosmos, a force that ensures the universe remains vibrant, complex, and capable of fostering life. Imagine a universe where spin is recognized as a primary interaction, a foundational law that dictates not just how things move, but why they exist in their particular dynamic state. It would elevate spin from a characteristic to a cosmic imperative, a constant presence that ensures the universe doesn't simply exist, but to perpetual evolving motion. It's a provocative idea, one that challenges our existing paradigms and invites us to look at the universe with fresh eyes, to see the ubiquitous world not as a mere phenomenon, but as a fundamental pillar of reality. As we stand here, gazing into the profound implications of spin, it becomes clear that our journey is far from over. Each answer we uncover only leads to a cascade of new, more intriguing questions. The universe, in its infinite wisdom, reveals its secrets in layers, each more astonishing than the last. We've explored the origins of spin, its necessity, its role in defining time and destiny, and now its potential connections to information, multi-dimensional realities, and even as a fundamental interaction. But what about the practical side? How do we detect these subtle twists and turns? How do we measure the spin of distant galaxies or the quantum spin of particles? What cutting-edge research is being done right now to probe these deeper mysteries? And how might we, as a species, learn to harness or even understand the power of spin in ways that could transform our future? These are the questions that will propel us forward as we continue to unravel the eternal, intricate ballet of rotation that defines our existence. The universe is a symphony of perpetual motion, and we are but a single spinning note within its grand composition. And the more we listen, the more we learn, the more we realize that the greatest secrets are often hidden in plain sight, perpetually, beautifully spinning. Join me next time as we dive into the fascinating world of spin detection and the ongoing scientific quest to fully comprehend this most fundamental of cosmic phenomena. Until then, keep wondering, keep exploring, and remember, you are spinning, and that, my friends, is truly magnificent. We've journeyed through the mind-bending implications of spin, contemplating its role in the arrow of time, its potential as a fundamental unit of information, even its whispers in the fabric of consciousness and the multiverse. We've dared to wonder if it might be a gateway to hidden dimensions, a fifth fundamental interaction yet to be fully uncovered. The sheer scope of these ideas, I know, can leave you feeling as though the universe itself is performing a dizzying pirouette right inside your skull. But how do we move from these grand, speculative conjectures to tangible evidence? How do we know the universe is spinning in these intricate, profound ways? What tools do we, as curious inhabitants of this perpetually rotating cosmos, employ to detect, measure, and ultimately understand this ubiquitous cosmic dance? Today, we're going to ground ourselves in the remarkable ingenuity of scientific discovery, exploring the incredible ways we peel back the layers of spin, from the colossal swirl of galaxies to the elusive twirl of subatomic particles. We're going to dive into the cutting-edge research that continues to unravel the universe's obsession with rotation, transforming abstract theories into measurable realities. What nobody tells you explicitly is that our understanding of spin is built upon a foundation of ingenious observation and experimentation. We don't just assume the universe is spinning. We see it, we feel its effects, and we measure its presence with ever-increasing precision. Let's start with the most visually stunning manifestations of spin, the macroscopic whirlwinds of the cosmos. When you gaze upon a breathtaking image of a spiral galaxy, you're looking at billions of stars, gas and dust, all locked in a majestic gravitational ballet, orbiting a central core. But how do we know it's spinning? We don't have a giant cosmic stopwatch to time its rotation directly. Instead, we use the incredible phenomenon of the Doppler effect. Just as the pitch of a siren changes as it moves towards or away from you, the light emitted by stars and gas clouds shifts in wavelength. Stars on one side of a galaxy, rotating towards us, appear slightly bluer, blue-shifted, while those on the opposite side, rotating away, appear slightly redder, red-shifted. By meticulously mapping these shifts across a galaxy, we can construct its rotation curve, revealing not only its spin speed, often hundreds of kilometers per second, but also, crucially, providing some of the strongest evidence for the invisible influence of dark matter, which dictates the outer regions of these spinning behemoths. Without dark matter, these galaxies would simply fly apart, unable to maintain their incredible rotational coherence. Zooming in a bit, we observe the spin of individual stars and planets. Our own Earth, as you know, spins at roughly 1,000 miles per hour at the equator, a fact we detect and confirm daily through the rising and setting of the sun, the precise timing of satellites, and even the subtle Coriolis effect that shapes weather patterns. For distant stars, we infer rotation by observing variations in their brightness caused by star spots rotating in and out of view. or by broadening of their spectral lines due to the Doppler effect across their surface. Some stars, like rapidly rotating pulsars, are spinning so fast, hundreds of times per second, that their precise rhythmic flashes of radio waves become cosmic lighthouses, their spin a critical component of their very existence. But the real magic of spin detection often happens at scales far beyond our direct perception, in the quantum realm. Here, spin isn't a physical rotation in the classical sense, but an intrinsic fundamental property of particles, like mass or charge. It's a quantum number that dictates how a particle behaves in a magnetic field. The groundbreaking Stern-Gerlach experiment in the 1920s was the first to unequivocally reveal this bizarre quantized spin. Imagine sending a beam of silver atoms through an inhomogeneous magnetic field. Classically, you'd expect the beam to spread out continuously, depending on how each atom's magnetic moment aligns. Instead, the beam split into two discrete paths. This was a monumental discovery, demonstrating that the electron spin isn't continuous. It's either spin up or spin down, quantized to specific values. It's like the universe's most fundamental coin toss, but with profound implications. This understanding of quantum spin is not just theoretical, it underpins technologies you might use or benefit from every day. Think about magnetic resonance imaging, MRI. What is MRI but a sophisticated detector of nuclear spin? The nuclei of atoms, particularly hydrogen atoms, abundant in our bodies, possess a property called nuclear spin which makes them act like tiny bar magnets. When placed in a strong magnetic field, these tiny magnets align themselves. By then blasting them with radio waves, we can flip their alignment. When the radio waves are turned off, the nuclei relax back to their original alignment, emitting their own radio signals in the process. Different tissues with different compositions and environments cause these signals to vary, allowing doctors to construct incredibly detailed images of soft tissues within your body. It's a testament to the power of understanding spin at its most fundamental level. Moving further into the realm of the subtle and indirect, we arrive at the most extreme spinning objects in the universe: black holes. How do you detect the spin of something that doesn't emit light and warps space-time itself? We do it by observing its profound influence on its surroundings. We revisit the concept of frame dragging, which we discussed earlier, as a consequence of spin. A spinning black hole literally drags the fabric of space-time around it, creating a current in the cosmic ether. This dragging effect has observable consequences. For instance, matter spiraling into a spinning black hole can have its orbital planes twisted and precessed, an effect we can sometimes glimpse in the jets of material ejected from active galactic nuclei. Even more dramatically, the merger of two black holes, or two neutron stars which are incredibly dense, rapidly spinning stellar remnants, creates ripples in space-time itself, gravitational waves. The incredible detectors of LIGO and Virgo, and soon Kagra and Lisa, have opened a new window into the universe, allowing us to hear the cosmic symphony of these violent collisions. What's truly mind-blowing is that the gravitational waves emitted during these mergers carry a unique signature of the south spins of the merging objects. The way the waveform chirps, the frequency, the amplitude, all encode information about the masses, orientations, and crucially, the angular momentum of the colliding bodies. The final ring-down phase, as the newly formed black hole settles, is like a cosmic fingerprint, revealing its final spin. This is a direct, awe-inspiring detection of spin in its most cataclysmic form, allowing us to measure the spin of black holes billions of light years away. And then there's the universe itself. We've talked about the universe being born to spin, its initial rotational whispers stretched by cosmic inflation. Can we detect this primordial spin? Scientists are tirelessly searching for subtle patterns in the cosmic microwave background, CMB, the faint afterglow of the Big Bang. Specifically, they're looking for a particular type of polarization pattern known as B-modes. While B-modes can be generated by gravitational lensing from intervening matter, a distinct swirl pattern in the CMB's polarization could be the smoking gun evidence for primordial gravitational waves, ripples in space-time from the very earliest moments of the universe. These primordial waves, if detected, would be direct evidence of the violent, energetic process that shaped the universe, potentially carrying the imprint of an initial cosmic vorticity, a universe with a preferred direction of spin on the largest scales. It's like searching for the ghostly echo of the universe's first pirouette. These incredible detection methods are not just academic exercises. They fuel a vibrant landscape of current scientific research pushing the boundaries of our understanding. In the realm of quantum technology, spin is the star of the show. We're on the cusp of a quantum revolution, and the manipulation of electron and nuclear spin is central to it. Quantum computers, for example, often use the spin states of electrons or atomic nuclei as their fundamental bits of information called qubits. The ability to precisely control and entangle these spin states holds the promise of solving problems currently intractable for even the most powerful supercomputers. This field, known as spintronics, aims to develop electronics that utilize not just the charge of electrons, but also their spin, potentially leading to faster, more energy-efficient devices. Imagine a future where your phone's memory stores information not as electrical charges, but as the up or down spin of individual electrons. Astrophysicists are relentlessly pursuing the secrets of cosmic spin. Current research focuses on refining our measurements of black hole spin, as this property is crucial for understanding how black holes grow, how they launch powerful jets of plasma that influence galaxy evolution, and even how they warp space-time in their immediate vicinity. X-ray telescopes observe the distorted light from matter orbiting close to black holes, looking for specific spectral line profiles, like the iron K-alpha line, that are broadened and redshifted by the extreme gravitational and rotational effects. Gravitational wave astronomy continues to expand its catalogue of black hole and neutron star mergers, providing an unprecedented wealth of data on their spins and how they evolve. Every new detection refines our models of stellar evolution and the most extreme events in the universe. Cosmologists, meanwhile, are not only looking for those elusive B-modes in the CMB, but also investigating the possibility of a large-scale cosmic vorticity, or rotation of the entire observable universe. While current data suggests the universe is remarkably isotropic, the same in all directions, the possibility of a subtle global spin remains an intriguing area of research, potentially offering profound insights into the very earliest moments of creation and the fundamental geometry of space-time. And the search for new fundamental physics, spurred by the profound nature of spin itself, continues unabated. Could spin be the key to unlocking the mysteries of dark matter? Some theoretical candidates for dark matter particles possess a specific spin. Experiments around the world are designed to detect the faint interactions of these particles, potentially revealing their spin signatures. And the audacious idea we touched upon in Chapter 6, that spin might be a fifth fundamental interaction, is not entirely off the table. Scientists are conducting ultra-precise measurements of forces at tiny scales, looking for any deviation from known physics that might hint at a new, spin-dependent interaction. The interaction of spin with gravity. particularly in the extreme environments near black holes, is also a fertile ground for testing Einstein's theory of general relativity and exploring theories of quantum gravity. The quest to understand why everything in the universe is spinning is, in essence, the quest to understand the universe itself. From the macroscopic spirals of galaxies to the quantum dance of particles, spin is a universal constant, a fundamental thread woven into the very fabric of reality. Our ability to detect and measure it through ingenious experiments and cutting-edge observatories is a testament to human curiosity and our insatiable drive to explore the unknown. As we stand on the precipice of new discoveries armed with technologies that allow us to peer into the heart of spinning black holes and listen to the echoes of the Big Bang, we are constantly refining our understanding of this pervasive phenomenon. The universe is not just spinning, it's revealing its secrets through its spin, inviting us to delve deeper into its eternal intricate ballet of rotation. And I'm always curious, what new spin-related mysteries will you help us unravel? We've journeyed through the cosmos, from the familiar rotation of our home planet to the mind-bending spin of black holes, and peered into the quantum realm where particles dance with an intrinsic angular momentum. We've seen how spin, this fundamental twist in the fabric of existence, is not just a cosmic quirk, but the very architect of the universe, defying gravity's collapse and shaping everything we know. We've even explored the cutting-edge ways we detect and measure this pervasive phenomenon, from the Doppler shifts of distant galaxies to the B-mode polarization of the cosmic microwave background. But as we stand at the precipice of our understanding, looking out at the swirling tapestry of the universe, a deeper, more profound question inevitably arises. Why? Why is the universe so utterly obsessed with spinning? Why this eternal intricate ballet of rotation? What nobody tells you explicitly is that the deeper we delve into the mechanics of spin, the closer we get to the edge of what science can currently explain, and the more we enter the exhilarating, sometimes unsettling territory of philosophical inquiry and speculative physics. We've traced the conservation of angular momentum back to the Big Bang, to the tiny quantum fluctuation stretched into a primordial twist. But what if that initial twist wasn't just a random event, but an inherent fundamental property of reality itself, a cosmic imperative? Imagine for a moment that spin is not merely a consequence of collapsing matter or a property of particles, but a foundational language of the universe. What if it's how the cosmos communicates, stores information, and perhaps even thinks? This brings us to one of the most exciting and truly mind-bending speculative connections, the idea that quantum spin is a fundamental unit of information. Think about it. A particle's spin can be up or down, a binary state much like the bits in a computer. In the strange world of quantum mechanics, a particle can even be in a superposition of both states simultaneously, until observed holding more potential information than a classical bit. This isn't just a neat analogy, it's the very bedrock of quantum computing, where qubits leverage spin to perform calculations far beyond classical limits. If spin is a fundamental carrier of information, then the universe, in its perpetual whirl, is an unimaginably vast, constantly processing cosmic computer. Every rotating galaxy, every spinning star, every electron orbiting an atom, every proton within that electron, they are all contributing to an immense distributed information network. Could the collective intricate spin of all particles, all systems, all structures be more than just physical motion? Could it be the very substrate upon which consciousness itself is built? This is where we venture into truly uncharted territory. If information is fundamental and spin is the language of that information, then it's not a stretch, though it is a leap, to wonder if consciousness, in its most basic form, is an emergent property of complex, organized spin states. Are our thoughts, our perceptions, our very sense of self, merely incredibly intricate patterns of spin, echoing the cosmic dance on a neurological scale? It's a thought that makes the hairs on your arm stand up, isn't it? To think that the same fundamental principle driving the birth of stars might also be humming within the neurons of your brain, allowing you to ponder these very questions. But the story of spin gets even stranger when we consider its interaction with space-time itself. We've talked about frame dragging, the way a massive spinning object twists the fabric of space-time around it, like a spoon stirring honey. This isn't just a theoretical curiosity, it's a measurable effect, confirmed by missions like Gravity Probe B. But what if frame dragging is more than just a local distortion? What if it's a subtle, yet profound gateway to something more? Imagine space-time as a vast, multi-layered tapestry. We perceive 3 spatial dimensions and 1 of time, but string theory and other models propose the existence of extra hidden dimensions, curled up so tightly we can't detect them directly. What if the twisting generated by frame dragging, by the ceaseless spin of everything, is subtly tugging at these hidden dimensions, creating ripples or connections that we are only beginning to glimpse? Could the spin of black holes, for instance, be creating microscopic wormholes or gateways to other universes through the extreme warping of space-time? Could the universe's inherent twist be a constant gentle pressure on these hidden realms, a ghostly echo of the cosmic whirl that permeates beyond our perceived reality? This isn't just science fiction, it's the frontier of theoretical physics. Researchers are actively exploring how spin might interact with gravity in ways we don't yet fully understand, potentially revealing new aspects of space-time geometry, or even opening up the possibility of travel through these warped regions. The universe's obsession with spinning might be its way of hinting at its own multi-dimensional complexity, a constant reminder that there's more to reality than meets the eye. And then there's the truly audacious hypothesis. Could spin itself be a 5th fundamental interaction? We have gravity, electromagnetism, and the strong and weak nuclear forces. These 4 forces govern everything we observe, from the orbit of planets to the decay of atoms. But what if spin, in its ubiquitous presence and its profound effects, is not merely an outcome of these forces, but an independent, equally fundamental interaction? If spin were a fundamental force, it would mean there's a unique spin field permeating the universe, mediating interactions between particles based on their angular momentum. It wouldn't just be about how matter collapses or how particles align. It would be about a direct, intrinsic force dictating how everything twists and interacts through that twist. This hypothetical spin force could manifest in subtle ways, perhaps influencing the distribution of dark matter, explaining anomalies in galactic rotation curves that currently require vast amounts of unseen matter, or even providing a deeper explanation for the mysterious arrow of time. Imagine a universe where the very act of spinning generates a force that influences other spinning objects, distinct from gravity or electromagnetism. It would add an entirely new layer to our understanding of cosmic dynamics, a new set of rules in the universal game. This is the kind of bold thinking that drives scientific progress, pushing us to question our most basic assumptions about the cosmos. We started this journey by feeling the subtle rotation of our own planet, the gentle pull of the Coriolis effect. We expanded our view to the dizzying speeds of our galaxy, then to the entire universe, a symphony of perpetual rotation. And now, We're asking if this symphony is not just a beautiful arrangement of notes, but a profound message encoded in every twist and turn. The ghostly echo of the cosmic whirl, as we called it, originating from the earliest moments after the Big Bang, is more than just a historical artifact. It's the universe's primordial signature, an initial twist that has reverberated through every subsequent cosmic event. This initial spin isn't just a starting condition, it's a constant underlying hum, an enduring resonance that defines the very character of our reality. It's the universe telling us, in its own grand, silent way, that stillness is an illusion and dynamism is the ultimate truth. So what does all this mean for us, the curious observers on a tiny spinning speck in an infinitely spinning cosmos? It means that you are not merely a static observer. You are an integral, spinning part of this magnificent, ongoing cosmic ballet. The atoms that make up your body are spinning, your planet is spinning, your solar system is spinning, your galaxy is spinning, and the entire universe is expanding and twisting in ways we are only beginning to comprehend. You are quite literally made of stardust and cosmic spin. This understanding profoundly shifts our perception of reality. It replaces a static, predictable universe with one that is vibrantly alive, constantly in motion, and deeply interconnected through this fundamental principle of rotation. It invites us to see the universe not as a collection of isolated objects, but as an intricate, dynamic system where every spin, every twist, every rotation contributes to the grand, unfolding story of existence. The journey to understand spin is far from over. Future generations of scientists, armed with ever more sensitive instruments and imaginative theories, will continue to unravel its deeper secrets. They will search for more definitive evidence of primordial spin in the cosmic microwave background. They will refine our understanding of black hole dynamics and frame dragging, perhaps unlocking pathways to new physics. They will push the boundaries of quantum computing, harnessing spin to solve problems we can barely conceive of today. And perhaps, just perhaps, they will confirm whether spin truly is a fundamental unit of consciousness, a gateway to hidden dimensions, or even the long-sought fifth fundamental force. For now, we are left with a profound sense of awe, a renewed wonder at the universe's elegant complexity. We have journeyed to the edge of the known, peered into the speculative, and come back with a deeper appreciation for the simple yet profound truth. Everything spins. It's not just a physical phenomenon. It's a cosmic imperative, a fundamental aspect of reality that underpins structure, carries information, and perhaps holds the keys to consciousness, hidden dimensions, and even forces yet undiscovered. So the next time you look up at the night sky, or even just feel the solid ground beneath your feet, remember you are part of a universe that is forever turning, forever twisting, forever dancing. And in that perpetual motion, there is a mystery, a beauty, and a truth that continues to inspire our deepest curiosity. We are all, in our own way, a part of the universe's magnificent eternal whirl. And that, my friends, is truly mind-blowing. We've journeyed from the familiar spin of our own planet to the mind-bending rotation of black holes, from the quantum whirl of subatomic particles to the grand cosmic ballet of galaxies. We've unravelled the elegant physics of angular momentum, traced the primordial twist back to the Big Bang, and even dared to speculate about spin as a fundamental unit of information, a gateway to hidden dimensions, or even an undiscovered fifth fundamental interaction. But how do we bridge the gap between these awe-inspiring hypotheses and the tangible, verifiable universe we inhabit? How do we prove that spin isn't just a consequence, but perhaps a cause, a primary architect of reality itself. This is where the cutting edge of science truly begins to blur the lines between physics and philosophy, between what we know and what we are only just beginning to imagine. It's a frontier where our instruments become extensions of our deepest curiosities, probing the very fabric of existence for whispers of the universe's most profound secrets. Consider the audacious idea that spin could be a fifth fundamental interaction. If it exists, it's not a subtle force, it's a pervasive, intrinsic property that should leave a signature, however faint, across all scales. But how do you detect a force that might be intrinsically linked to the very geometry of space-time, or to the quantum information encoded within matter? What nobody tells you explicitly is that searching for such a force isn't about finding a new particle in a collider, though that's certainly one avenue. It's about looking for anomalies. Imagine ultra-sensitive experiments, shielded from every known interference, designed to measure the spin interactions of particles with unprecedented precision. We're talking about quantum-level measurements, where the slightest deviation from the predictions of the Standard Model, our current best understanding of fundamental particles and forces, could hint at something more. Perhaps a tiny, inexplicable torque between two spinning particles separated by a vacuum, or a subtle influence on the decay rates of certain isotopes that can't be accounted for by gravity, electromagnetism, or the strong and weak nuclear forces. It's like searching for a ghost in a meticulously catalogued library, where every book, every shelf, every dust mote has a known explanation. If you find something that defies classification, that's your starting point. These are the kinds of experiments being designed right now, pushing the boundaries of what's possible in laboratories around the world. We're talking about exquisitely sensitive atomic interferometers, levitated optomechanical systems, and even proposals to use neutron stars as natural laboratories, where their immense density and rapid spin could amplify the effects of a hypothetical spin force to detectable levels. The challenge is immense, the signal-to-noise ratio often daunting, but the potential reward, redefining our understanding of the universe, is absolutely worth it. Then there's the mind-bending concept of spin as a fundamental unit of information, a cosmic qubit. If the universe truly is a vast, spinning, computing system, how do we tap into its operating system? How do we detect these cosmic qubits and their entanglement across vast distances? This is where the burgeoning field of quantum computing itself becomes a research tool for cosmic inquiry. We're not just building quantum computers to solve complex problems, we're using them to understand the fundamental nature of information and entanglement. By pushing the limits of quantum coherence and entanglement in our labs, we hope to gain insights into how such phenomena might manifest on a universal scale. Could we detect patterns of quantum entanglement in the cosmic microwave background that are too complex to be explained by simple thermal fluctuations? Could there be subtle, non-local correlations in the spin states of distant particles that defy classical explanations, pointing to a universe where information is intrinsically linked through a web of spin? The search for these cosmic qubits also takes us to the realm of quantum gravity. If space-time itself is quantized, perhaps the fundamental pixels of reality, these smallest units of space-time, possess an intrinsic spin that encodes information. Theories like loop quantum gravity, which posits that space-time is woven from tiny loops, and string theory, where fundamental particles are vibrating strings, inherently deal with spin at their most basic level. These theoretical frameworks are our maps, guiding us to look for specific signatures, perhaps in the fine structure of gravitational waves, or in the energy spectra of high-energy cosmic rays interacting with the vacuum itself. The detection methods here are often indirect, requiring us to infer the presence of these quantum information units from their macroscopic effects. And what about Yao's spin as a gateway to hidden dimensions or the multiverse? We briefly touched on frame dragging, where spinning masses twist space-time. If there are extra dimensions, perhaps this twisting isn't confined to our familiar four-dimensional space-time. Perhaps a spinning black hole could drag or distort these hidden dimensions, creating ripples that might, however faintly, propagate into our observable universe. Detecting this is a monumental task. One promising avenue lies in the advanced gravitational wave astronomy. Our current detectors, like LIGO and Virgo, are already revolutionizing our understanding of the cosmos by observing black hole mergers and neutron star collisions. But as these detectors become even more sensitive, and as new observatories come online, like LISA, a space-based interferometer, we'll be able to probe gravitational waves with unprecedented precision. Imagine analysing the gravitational wave signals from merging supermassive black holes at the centres of galaxies. If these black holes are spinning rapidly, and if their spin influences hidden dimensions, could there be subtle, unexpected distortions in the waveform? Could the ring-down phase, the final moments as the newly formed black hole settles, reveal gravitational modes that don't fit the standard predictions of general relativity, hinting at energy leaking into or from other dimensions via their spin? It's like listening to a perfectly tuned symphony and suddenly hearing a note that shouldn't be there, a ghostly echo from another room. Furthermore, high-energy particle collisions at accelerators like the Large Hadron Collider LHC are also crucial. If extra dimensions exist, and if spin is somehow connected to them, we might observe particles disappearing from our dimensions, carrying energy and momentum with them, only to reappear as subtle missing energy signatures. Or, conversely, we might detect exotic particles that are typically confined to these hidden dimensions, briefly manifesting in our own spacetime due to extreme spin-induced distortions. The detection of micro-black holes, or other exotic phenomena, predicted by some theories of quantum gravity, could also be indirect evidence of such spin dimension connections. The search for primordial spin in the early universe, via the B modes of the cosmic microwave background, CMB, remains a cornerstone of this quest. While B modes are primarily sought as evidence of primordial gravitational waves, which themselves are linked to the stretching and twisting of spacetime during inflation, advanced analysis of CMB polarization could reveal even subtler patterns. Could there be a cosmic vorticity imprinted on the CMB, a large-scale rotational pattern that speaks to an intrinsic fundamental spin of the entire universe beyond what standard models predict? This would be a direct measurement of the universe's initial twist, an echo of the cosmic ballet's very first pirouette. Experiments like the Simons Observatory and CMBS-4 are pushing the boundaries of this detection, aiming for the precision needed to uncover these elusive signatures. What truly unites all these diverse research fronts is the relentless pursuit of the ultimate why. Why is everything spinning? We've moved beyond merely describing the phenomenon to actively seeking its deepest roots, its most profound implications. From the quantum laboratories on Earth to the vast reaches of space where gravitational wave detectors listen to the universe's whispers, scientists across the globe are united in this cosmic detective story. We are, in essence, trying to read the universe's instruction manual to understand the fundamental code that governs its existence. And at every turn, at every scale, spin emerges not as a mere side effect, but as a central character in this grand cosmic narrative. It's the engine, the information carrier, perhaps even the key to unlocking hidden realities. As we stand at this precipice of discovery, peering into the universe's spinning heart, we are reminded that our understanding is always evolving, always expanding. The questions we ask today are bolder than ever before, fueled by an insatiable curiosity and ever more sophisticated tools. We're not just observing the spin, we are actively trying to understand its purpose, its origin, and its ultimate destiny. And in doing so, we are not just learning about the universe, we are learning about ourselves, our place within this eternal, intricate ballet of rotation. The next chapter, my friends, brings us to the most profound question of all. What does this pervasive, inescapable spin mean for us? What does it mean to live in a universe obsessed with spinning? And how does it redefine our very concept of stillness and existence? Prepare to have your perceptions of reality once again challenged and expanded. We've journeyed through the cosmos, from the infinitesimal dance of subatomic particles to the grand ballet of merging galaxies, all united by one relentless, omnipresent force, spin. We've peeled back layers of mystery, from the conservation of angular momentum to the primordial twist of the Big Bang, from spin's role in preventing collapse to its potential as a fifth fundamental interaction. We've even dared to consider it as the universe's inherent language, a cosmic qubit, or a gateway to unimaginable dimensions. But now, it's time to bring this vast, mind-bending cosmic narrative home. What does this incessant, inescapable, fundamental spin mean for us? For our lived experience, our perception of reality, our very sense of self, you are spinning. Right now. You know this intellectually, of course. Earth is rotating at roughly 1,000 miles per hour at the equator, hurtling around the Sun at 1,000 miles per hour, which itself is orbiting the galactic centre at a blistering 514,000 miles per hour. And the entire Milky Way is rushing through intergalactic space, caught in the gravitational pull of the Laniakea supercluster, all part of an even grander cosmic flow. We're not just passengers on a spinning rock, we are made of spinning particles, our very atoms a whirlwind of electrons, protons and neutrons, each possessing their own intrinsic quantum spin. Every cell in your body, every thought in your mind, every beat of your heart is a product of this intricate nested symphony of rotation. Yet we perceive stillness. We sit, we stand, we lie down, and we feel stationary. This, my friends, is one of the universe's most profound and elegant illusions. It's the shared inertia that binds us, the collective momentum that makes us feel grounded. Because everything around you is spinning at precisely the same rate, in the same direction, relative to your immediate frame of reference, your senses are tricked into believing in a stable, unmoving foundation. But what nobody tells you explicitly, what truly grasping this cosmic truth reveals, is that stillness is not a state of being. It's a momentary relative agreement, a fleeting perception within an overwhelmingly dynamic reality. Imagine, for a moment, if you could truly feel the spin. Not the dizzying sensation of a carnival ride, but the deep, resonant hum of the Earth's rotation beneath your feet. The subtle warp of space-time as our solar system carves its path. The quantum hum of your own cellular machinery. Would it change how you walk, how you breathe, how you perceive time itself? Would you feel more connected, or perhaps overwhelmingly insignificant? The truth is, whether we feel it or not, this spin profoundly shapes who we are. Think about the very structure of your being. Your DNA, that magnificent double helix, is a spiral, a molecular spin. The proteins that form your tissues, the neural pathways that spark your consciousness, all emerge from the interactions of spinning particles. Your very existence is an emergent property of countless tiny coordinated spins. We are, in essence, walking, talking, thinking embodiments of angular momentum. We are the universe's spin made manifest, experiencing itself. This realization isn't just a scientific curiosity, it's a philosophical earthquake. If spin is so fundamental, so pervasive, so intrinsically woven into the fabric of reality, then it must influence our consciousness, our perceptions, our very understanding of existence in ways we're only just beginning to fathom. Could our internal spin, the electrical impulses firing through our brains, the quantum coherence within our neurons, be echoing or even resonating with the cosmic spin? Some highly speculative theories, venturing into the realm of quantum consciousness, suggest that the brain might exploit quantum phenomena, including particle spin, to generate the complex emergent properties we call thought and awareness. If this is even partially true, then our minds are not just observing the spinning universe, they are, in a very real sense, participating in its spin, a microcosm mirroring the macrocosm. Our thoughts, our decisions, our very sense of self could be intricately linked to this grand universal gyre. This deep connection to the universe's spin also challenges our anthropocentric view of reality. We tend to place ourselves at the centre, observing a static backdrop. But the universe is a living, breathing, spinning entity, and we are not merely observers but active participants, woven into its very texture. Our perception of time, for instance, might be inextricably linked to this universal dynamism. As we discussed, spin fuels entropy, driving the universe forward, defining the arrow of time. Perhaps our subjective experience of time's relentless flow is an internal reflection of this cosmic process, a personal awareness of the universe's ceaseless evolution through spin. What does it mean, then, to live in a universe obsessed with spinning? It means that stability is an achievement, not a given. It means that change, motion, and transformation are the fundamental truths. It means that every moment is a fleeting configuration in an eternal dance, a snapshot in a cosmic whirl. This perspective can be profoundly liberating. If stillness is an illusion, then perhaps our anxieties about change, our yearning for static permanence, are fundamentally at odds with the universe's true nature. Embracing the spin means embracing dynamism, flux, and the perpetual unfolding of reality. It means understanding that growth, evolution, and adaptation are not just desirable traits, but echoes of the universe's own operating system. Consider the implications for our future, for humanity's next great leaps. If we truly internalize the spinning nature of reality, how might it reshape our technology, our exploration, our very way of life? Imagine spacecraft designed not to merely resist the forces of spin, but to harness them, to utilize the inherent angular momentum of celestial bodies or even the space-time frame-dragging effects we explored. Perhaps future propulsion systems won't just push against inert space, but will learn to surf the cosmic currents, tapping into the rotational energy of the universe itself. This isn't science fiction, it's a logical extension of understanding spin as a fundamental interaction, a force to be reckoned with and potentially utilized. On a more profound level, this understanding could inform our search for life beyond Earth. If spin is a cosmic necessity critical for the formation of stars, planets, and the complex chemistry of life, then perhaps the signatures of spin, the rotational velocities of exoplanets, the stability of their orbits, the very twist in their nascent nebulae, could become key indicators in our hunt for habitable worlds. We might even find that certain types of spin are more conducive to the emergence of complex life, a cosmic filter we're only beginning to understand, but the ultimate why still lingers, doesn't it? We've explained how spin works, what it does, where it comes from in the Big Bang, and what it means for us. But the primal question remains, why? Why did the universe begin with that primordial twist? Why is it obsessed with this elegant perpetual motion? Perhaps the why isn't a simple answer, a single cause. Perhaps the why is not a destination but the journey itself. Maybe spin isn't just a consequence or a mechanism, but an inherent defining characteristic of existence, a fundamental axiom of reality that simply is. Could it be that the universe must spin to exist? That without this ceaseless dynamism, this constant redistribution of energy and momentum, the cosmos would simply collapse into a featureless singularity, unable to manifest the intricate beauty and complexity we observe? If so, then spin isn't just a feature, it's the very heartbeat of creation, the rhythm that allows reality to unfold. And if spin is that fundamental, then our human quest to understand it, to measure it, to harness it, is not merely an academic exercise, it's a profound act of self-discovery. By unravelling the mysteries of cosmic spin, we are, in a very real sense, coming to understand the deepest truths about ourselves, our origins, and our place in this vast, mind-boggling, perpetually rotating universe. The universe isn't just spinning out there, it's spinning within you. It's the silent engine of your existence, the unseen architect of your reality. And once you truly grasp that, once you feel that deep internal resonance with the cosmic gyre, your perception of stillness will forever be transformed. You'll understand that you are not a static observer, but a dynamic, integral part of the most magnificent, eternal, intricate ballet of rotation imaginable. You are the universe, spinning, and that, my friends, is a truth more profound, more beautiful, and more utterly mind-blowing than any single answer to the why could ever be. It's a truth that invites us not to merely observe, but to participate, to dance with the cosmos. As we stand on the precipice of even deeper understanding, with new telescopes gazing further into the cosmic dawn and quantum experiments probing the very fabric of space-time, we continue our relentless quest. We search for the elusive B-modes in the cosmic microwave background, the ghostly echo of that initial inflation-driven twist. We meticulously map the spin of black holes, hoping their rotational signatures will reveal secrets about dark matter, dark energy, or even the nature of gravity itself. We push the boundaries of quantum computing, dreaming of harnessing the intrinsic spin of particles to unlock unimaginable computational power. Each discovery, each new piece of data, adds another brushstroke to the grand canvas of universal spin. We are not just collecting facts, we are piecing together the ultimate story of existence, a story where spin is not a footnote but the central, driving narrative. So the next time you feel the solid ground beneath your feet, take a moment, close your eyes, and remember, you're not still. You're a vortex of motion, a symphony of spin, a living testament to the universe's most fundamental obsession. You are part of the cosmic dance, and the music, the eternal rhythm, is spin. What an extraordinary thought, what an extraordinary reality, and what an incredible journey we're on together, as we continue to unravel the universe's most profound secrets one spin at a time.